Hey Math 30, welcome back. And in this video, I'm just going to do a few more examples of L'Hopital's rule. One where we're given a graph, one example that's just a little bit longer to go over some things that pop up there, and another one where we could actually use the skills we learned in chapter 2. So it's a good review of those old ways of doing limits, which could be on the final, by the way. So we'll review an old way to do a limit, and then we'll use L'Hopital's rule to get the same answer. And so we'll see the same answer two different ways. Okay, so let's do this one. So this is the one that's actually kind of a throwback question. What's the limit as x goes to 3 of x minus 3 over x squared minus 9? So as always, first thing you should try is direct substitution and see what you get. So we put like a question mark here to say, does this equal what we get when we do direct substitution? Well, let's check. So it would be 3 minus 3 over 3 squared minus 9. And that is 0 over 0. So this is a no. This is not equal to that because what's on the blue stuff that's on the right-hand side is not a number. You can't have a limit equal to a thing that's not a number. But what this does mean is that the limit is indeterminate of type 0 over 0. Okay, so since it's indeterminate of type 0 over 0, we could use L'Hopital's rule, and L'Hopital's rule will work. But because this is a rational function and the denominator is factorable, we actually can use more basic methods, and that would be to factor and cancel. So let's do this one the old way. You remember that if you get an indeterminate form when you try direct substitution, then you can factor, and by the way, this factors as x minus 3. Well, actually, let me finish what I was going to say. If you get an indeterminate form, what that means is the limit might exist, the limit might not exist, the limit might be finite, the limit might be infinite. An indeterminate form basically says you don't know. You don't have enough information to know what the limit equals. So you need other approaches. One other approach we learned in chapter 2 was to factor and cancel. What we're learning in this chapter is to use L'Hopital's rule, which is an alternate form. L'Hopital's rule only works for certain types of limits if you have an indeterminate form. It doesn't work for all limits. And some of the chapter 2 techniques don't work in the cases where L'Hopital's rule works. So you need all these different tools. Okay, so this cancels, and we are left with a limit as x goes to 3 of 1 over, sorry, that should have been plus. It factors as x minus 3x plus 3. So the denominator will be x plus 3. And now I can do direct substitution, and this equals will be true because this will be 3 plus 3, which is 1/6. So the answer is 1/6. Let's verify that using L'Hopital's rule. So L'Hopital's rule says that we can replace the original limit with the limit of the derivatives of the numerator and denominator. And the derivative of the numerator is 1. The derivative of the denominator is 2x. So we've done the derivative. We've done dx and dx. And okay, so now notice this is not the same. So these two limits are not the same thing. So the first approach and the second approach don't end up with the same limit that you're going to evaluate, but L'Hopital's rule guarantees that you'll get the same answer. And now we can do direct substitution. And direct substitution gives us 1 over 2 times 3, which is 1/6. So either method gives you the same answer in this case. Okay, let's look at one that's similar to what's on your homework, and this is a L'Hopital's rule question that uses a graph. So it's going to force us to think about old meanings of the derivative. Okay, use the graph of f and g. Use the graphs of f and g and their tangent lines at 2, 0 to find the limit as x goes to 2 of f divided by g. So the first thing we need to check is, well, you could actually try direct substitution. So what is this? What is f of 2 over g of 2? Well, this point here is 2. Let me switch colors because they're using blue. This point here is 2, 0. So this limit, or if I try direct substitution, I get 0 over 0. So, and we can see that the functions, the limit of g approaches 0 from the right and from the left. G is the blue graph. F is the red graph. F approaches 0 from the right and the left. These f and g both are equal 0 right at the same spot at 2. So what we get is an indeterminate form of type 0 over 0. So what we can do is, instead of evaluating this limit, we can evaluate the limit of the derivatives. F prime of x and f prime of g. G prime of x. Okay. Now, what is that? Well, we can actually try direct substitution again, but now with the derivatives. And this time it's going to work. So in the picture, do you notice that they have graphed the tangent lines at 2? Let's remind ourselves, f prime at 2 means the slope of the tangent line of f at x equals 2. So this numerator here is the slope of f at 2, which is the red tangent line of f at 2. And the slope of that is found right up here because this is the equation of that tangent line. And the slope is 1.8. So f prime at 2 is 1.8. Similarly, the slope of g is the slope of the blue tangent line because this blue tangent line is tangent to g right at 2. And the slope of that line is 4/5. And I'll just off screen do a little Desmos scientific here, and I'll just do 1.8 divided by, I don't know why I wrote 4.5. That is 1.8 divided by 4/5. And we get 2.25. Two and a quarter. Okay, cool. So that's that. We have calculated that one. So this was in case of indeterminate. And because we had the equation of the tangent lines, we could use the slope of the tangent lines to figure it out. You're going to have a few in your homework where there's graph ones where you need to use the graph. Okay, here's kind of a longer example. We're going to work through it. And sometimes you just got to apply L'Hopital's rule multiple times. So first things first, if we try direct substitution, we get which is which would give you, which is 0 over 0. So it's indeterminate of type 0 over 0. Now remember, that doesn't mean anything. That doesn't mean anything. So I'm not writing the equals, but I'm just checking that when you do direct substitution, you get 0 over 0. The formal way to write it would be to write the limit as x goes to 0 of tangent x minus x equals 0. And the limit as x goes to 0 of x cubed equals 0. So it is indeterminate of type 0 over 0. Okay, on the final exam, if you have a problem where you're doing L'Hopital's rule, make sure to write this. Make sure you can't apply L'Hopital's rule unless you show that it is an indeterminate form. So you need to show that the limit of the numerator is either 0. You need to show the limit of the numerator, show the limit of the denominator, and you need to either get 0 over 0 or infinity over infinity or negative infinity over infinity. You can get negative infinities, that's fine, but you either need 0 over 0 or infinity over infinity, or it could be negative. Okay, so we can start doing this. So the limit as x goes to 0 of tangent x minus x over x cubed will be equal to the limit as x goes to 0 of secant squared x minus 1 over 3x squared. And just to kind of like not write everything out every single time, I'm going to just show that, hey, secant squared x, secant squared of 0 minus 1 is, by the way, secant squared is 1 over cosine squared. So this is 1 over cosine squared of 0 minus 1. Well, cosine of 0 is 1, so this is 1 over 1 minus 1, so this is 0. 3 times 0 squared is 0. So can you see that this numerator, the limit of the numerator is 0. The limit of the denominator is still 0. So we're still getting 0 over 0 when you do direct substitution on the top and on the bottom. So that means we can apply L'Hopital's rule again. So that means this equals the limit as x goes to 0 of, now secant squared, that's secant with a square on the outside. So when we do the derivative of the top, that's going to be 2 times secant x to the power of 1. It's power rule. But then you multiply by the derivative of the inside, which is secant, so it's chain rule. And the derivative of secant is secant x tan x. Let me put another parentheses there. Okay, so just a little side note. Little side note of if y equals secant squared x, that's the same as secant x all squared. So then y prime is 2 secant x to the first times the derivative of secant, which is secant x tan x. Okay, so that's chain rule. So just to remind you, a little side note of how I got that derivative here in the numerator. And the derivative of the denominator is much easier. It's 6x. Okay, So if we try to do direct substitution again, let me just do this and make it a little bit smaller. Move that over here like that. So just side note again, if we tried to do direct substitution here, we would get 2 times secant of 0, which is 1, secant of 0, which is 1, tangent of 0, which is 0, over 6 times 0, which is 0 over 0. It's still indeterminate. This would be 1, 1, 0, and then over 0. Okay, so guess what? Do L'Hopital's rule again, and I need a little bit of room here. Limit as x goes to 0 of... Well, let me actually just kind of clean this up real quick. The numerator is secant squared x tangent x, and the denominator is 3x. Okay. Cool. So the 2 over 6 reduces to 1/3. And that is equal to, because we've already shown that that's an indeterminate form of type 0 over 0, you just got to do it again. The numerator is product rule. Derivative of secant is 2 secant x times secant tangent. So I just did right there, I just did the derivative of secant squared. It's the same as what we had before. And then now it's product rule, so I just copy the second factor. So this is the derivative of the first factor. That's the derivative of secant squared. This is just tan x by itself. Then I add secant squared x times the derivative of tangent, which is secant squared x. Now the derivative of 3x is 3. And now it's going to work because I've finally gotten to the case where the denominator is a constant. And now I can do direct substitution. This is 2 secant squared of 0 tangent of 0, tangent squared of 0. So I just did two things in one. Secant times secant is secant squared. Tangent times tangent is tangent squared. And I plugged in 0. Plus secant to the 4th of 0 all over 3. And I get 1/3, because this is because tangent of 0 is 0, so I get 0 plus 1 over 3, which is 1/3. And one way you can check this is by graphing it. So let's see. Let me do this. Let me make sure. And we'll check it graphically. Okay, so let's graph the original. I'm just going to graph f of x equals this, and we'll put in the original given, tan x minus x over x cubed. And we want to know the limit at 0. So you notice, so first off, do you notice at x equals 0, the graph is definitely reaching a finite value. There's no vertical asymptote. So, but we do know that it's undefined at 0. So if we actually tried to plug in f of 0, it would be undefined. But if you just slide this right onto there, the function is undefined. It doesn't know what to give you. So one way we can graphically check our answer is to actually plot the coordinates of our result. Now remember, our result was that the limit of this function is 1/3. So what that means is if we zoom in on this, we better see the function getting closer and closer and closer to 1/3. Notice the y coordinates of these points as I get closer and closer are getting, notice that that's getting closer to 0.33333. Sorry, let me make this a little bit bigger. Notice this is getting closer to 0.3333333. And this is getting closer to 0.333 on the left. So that's one way to determine it. And you can also visually see it by going 0, 1/3. That was our limit value we found. Let's make everything black just so they match. And then I'll make it a hole because I know it's a hole. There's a hole in the graph right at 0. Okay, so that's one way to calculate it. You can also use Wolfram Alpha. You can actually do things like find the limit, or what's the limit of, you just use the natural language, what's the limit of tan x minus x over x cubed at x equals 0, and it will do L'Hopital's rule for you and check your answer. But you need to be able to do it by hand. Okay, I just wanted to show you a couple more examples. It'll kind of help you maybe with a few of the problems on your homework, and that's it. I'll see you next time.